طيب بسم الله الرحمن الرحيم. So next time we talked about block coding, and we said that the purpose of block coding are two things, right? To enhance error detection and to enhance the self-synchronization issue. And we have seen that combining block coding with line coding scheme like NRZ with inversion can save some bandwidth compared to, for example, the biphase line coding scheme. So despite the fact that the block coding enhances the self-synchronization and the error detection, it does not help a lot, or maybe it reduces, but it does not eliminate completely the DC component. So we still have DC components in schemes like NRZI with the block coding. So DC component is still there. Also, if we consider something like AMI, AMI seems to have no DC component, right? AMI, as we discussed, which is like one is for, you can interpret one as inversion, so every time you change the voltage level, and 0 is no change. And that seems to be attractive from the bandwidth point of view. It seems to be attractive from the DC component point of view, because as we said, for 0, we interpret it as 0 voltage. So the power consumption in that case is 0. So the power level for low frequency component is 0, right? Which is attractive. However, this consecutive 0 pattern creates some kind of a problem with the synchronization. Okay? So let's go to biphase. Biphase seems to be attractive from the synchronization point of view. However, it's not so with respect to bandwidth, right? Because it doubles the bandwidth. So until now, we do not have a solution that addresses all the criteria that we talked about, even with block coding. Okay, so scrambling tries to complement the line coding schemes that have problem in synchronization. Okay, particularly AMI, which seems to be attractive from the bandwidth point of view and seems to have no DC component, but it has this consecutive 0 problem, which causes lack of synchronization. So what scrambling does is that it actually tries to substitute. It tries to substitute the consecutive 0 patterns with another pattern which eliminates the consecutive 0 issue so that we can enhance the synchronization. So this happens as a modified version of AMI, which uses scrambling as a complementary technique to replace the consecutive zeros with another pattern which can enhance the synchronization, as we will see in a minute. So what we need to do is to complement AMI with scrambling, particularly to get all the consecutive zeros and then replace them in such a way that's agreed upon between the sender and the receiver, and in such a way that does not actually confuse the decoding, right? Because guess what? Here I'm not encoding. I'm not replacing every 4 bits with 5 bits. No, I'm just replacing consecutive zeros with some signal levels. So I'm not coding before that. So I'm just taking the consecutive zeros and then I replace them with different voltage levels. But when I replace them with different voltage levels, this might confuse the receiver, right? Because the receiver might interpret these signal levels as different bits. And then it gets confused and decodes the data bits in a wrong way. So we need to do it carefully in such a way that instead of sending constant voltage 0, we send some different voltage levels, but the receiver has to be able to recognize these different voltage levels as this is not the actual data. This is just for scrambling. So you should decode this as consecutive zeros. You see what I mean? So I'm just trying to get away from the constant 0 voltage, okay, to enhance the synchronization. So let's see how this is done. So the first substitution technique or scrambling technique is what we call binary 8 serial 0. What this scrambling technique does is that it goes through the binary data, and then if it finds consecutive zeros, then it counts them until I count 8 consecutive zeros. That, as we said, generates some kind of a problem. So I need to do some substitution. Remember the AMI, what it does is that it says 0 will be interpreted as 0 voltage. Okay? So if I have 0, this means 0 voltage all the way. Okay? If it's 1, then I have to look at the non-zero voltage before me and invert that. So if it's positive voltage, then if I have 1, let's say here, then this needs to be negative. If this is negative, then this should be positive. And we said that this is good because if I have consecutive ones, then there's no problem because I have to invert all the time, and that creates the changing voltage level, which is good from the synchronization point of view. Okay, and this is the worst case when it comes to bandwidth, and we calculated that, and we have seen that the bandwidth is attractive, and this way we can eliminate the DC component. So what the scrambling technique does is that it says, okay, if I have consecutive zeros, particularly 8 zeros, what I'm going to do is that I'm going to interpret all these 8 consecutive zeros as follows. I'm going to substitute 8 zeros with 0, 0, 0, 3 zeros, so these are constant, okay? And then violation. V here stands for violation. I'm going to violate the normal sequence of AMI. Because AMI, what AMI says is that if I have 1, then the voltage level needs to be opposite of the previous non-zero voltage level, right? So if this is 1, then the voltage level here should be negative, right? So what the scrambling technique will do is that it will violate that by giving me a positive voltage level, not 0, not negative, because if it's 0, then I did not fix anything. If it's negative, then the receiver will say, this is a legitimate voltage level and it's opposite to the previous non-zero voltage level, so I'm going to interpret that as 1. The receiver will say, okay, so this is a negative voltage level and the previous one was positive, therefore this is 1. I don't want this to happen because the original bit is 0, not 1. معايا? Okay. So I'm going to violate the normal sequence of AMI. That's why it's called V or violation. So instead of sending negative voltage level, which might be interpreted by the receiver as 1, I'm going to send yet another positive voltage level. So this one is similar to this. Remember, V is not necessarily positive. V means violation. Okay? So V means violate. I'm going to violate the normal sequence of AMI. So if this is positive, I'm going to send positive. If this is negative, I'm going to send negative. To indicate to the receiver that, pay attention to the fact that this is not a legitimate voltage level that represents a particular data bit. No. This is done for scrambling. So the receiver will interpret this as a violation which indicates to the receiver that this is scrambling. Right? Since this violates the normal procedure of AMI, the receiver will say, okay, so we agree. So now we are doing scrambling. We're not doing normal data decoding. So it will say, starting from here, this is violation, and this is binary, which means that I'm going to toggle this voltage level, whatever this voltage level is. So violation, binary, 0, violation, binary. Okay? So B means that I'm going to toggle this. So if we were to, for example, if we were to have so like negative voltage, which indicates 1, and then 8 zeros. Okay? I'm going to use the exact same substitution. So here, I'm going to say, okay, the first 3 zeros, I'm going to interpret them as is. So until here, we have 0 voltage level. Then violation. Violation means that whatever that level is, I'm going to use the exact same level. This is V. So V here is negative. And then B, which is a positive, which is reverse of this. And then 0. Right? And then another violation, which is, what is the previous voltage level? Is positive. Then violation means that again it's positive. And then B, which is negative. So this is actually V, B, 0, V, B. Okay? So when the receiver reads that, it will find that the previous voltage level was negative. Okay? Here the previous voltage level was negative, and this is also negative, so this is not the normal procedure of AMI. This is the start of scrambling. So it will interpret all these bits as 0 and not anything else. So by doing this, what I essentially did is that I avoided the consecutive 0 voltage, which was causing a problem, okay, by creating different voltage levels. So this will definitely, the change in the voltage level will definitely enhance synchronization, right? صح? So instead of having constant voltage level of 0 for 8 consecutive bits, I created some kind of change which essentially enhanced the synchronization.
But it's always in this order.
Oh yes, yes, yes. 0, 0, 0, V, B, 0, V, B. The substitution is constant. The only difference is that how you interpret V. Okay? So V has to be in the same level like the previous non-zero voltage. And then B toggle. And then 0, and then V again, and then B. Okay? So the receiver will recognize this as scrambling, and then it will replace all the 8 bits with zeros. So during transmission, I actually enhanced the quality of transmission. How? Because DC component is not there, which is an inherent feature in AMI, which is good. The only problem here is synchronization. So by doing this change of voltage, I was able to enhance the synchronization. So the reception is better in terms of performance, and I did not create any kind of confusion by interpreting some of the zeros as ones or the other way around. Okay. So here I use the notion of the fact that if I have ones, I have to toggle the voltage level of the previous non-zero voltage, right? So by incorporating this violation concept, I was able to enhance the synchronization. It's a very simple idea. Okay? There is a slight problem in this. By the way, this technique is used a lot in North America. There is a slight problem in this technique, which is the fact that, I mean, remember here, I'm trying to always substitute with 4 different voltage level that are non-zero. Always, all the time. So 2 of them are negative and 2 are positive. And this is in fact good because again, our aim should be to try to balance the average voltage. Okay? Because that's another desirable thing to have, is to kind of balance the positive voltages and the negative voltages. This is good. So in the substitution, I have actually used 2 positive voltages and 2 negative voltages to try to have some kind of a balance. So I created a change, which is good for synchronization, and at the same time, I had 2 positive and 2 negative. Okay? The slight problem here comes that here we have 1 interpreted as negative, right? The previous one here is negative voltage, right? And then I have 2 positive voltages and 2 negative voltages. So the result after this substitution all the way is the fact that we have negative voltage, right? Here, in this example, we ended up having positive voltage. Okay? So even though I tried to balance within the substitution duration, but I did not take into consideration the previous voltage level. Okay? So is there any other alternative? Yes, there is a small input that considers this. I'm going to have 2 substitution possibilities. Okay? So this scheme, this is used, by the way, in outside of North America, like in Europe. This is used more in Europe. Okay? So what this tries to do is that it says, I'm going to have 2 substitution patterns. 2 substitution patterns. If the previous voltage level, the previous non-zero voltage level, okay, is even, then I'm going to replace with B00V. What this tries to do is that it creates some kind of a positive voltage level. Why? Because the previous voltage, the previous non-zero voltage level is even. If it's even, substitution patterns will be B00V. If it's odd, then the substitution pattern will be 000V. So what this tries to, so I have, this is called HDB3. It substitutes 4 consecutive zeros with one of these patterns. If it's odd, then I'm going to have V, which is one change. So because odd, I'm going to have one change. This means that the change is always even. And what this tries to do is to try to balance the up and the down voltage, to try to create some kind of a balance. So if the change is odd, I'm going to have only one change. If the change is even, I'm going to have 2 changes to make it even. Okay? So that's the only slight change in here, is that this scheme tries to take into consideration the previous change in the voltage level. So if the change in the voltage level is even, then I use one pattern. If it's odd, then I use another pattern, to try to keep the change in the voltage level always even. Okay? So for example, here I have 1 and then 1, which is created as non-zero voltage. So the result is that here I have even voltage level changes. So in that case, I go to here, I use B00V. And remember here, we do not substitute 8 consecutive zeros. We substitute only 4. Okay? So here, this scheme substitutes every 4 consecutive zeros, not 8. So this is more conservative, let's say. So this tries to be more conservative from 2 things. From the fact that I will not leave 8 consecutive zeros before I perform the substitution. I will do it at 4. And the other slight change is that I'm going to have 2 substitutions, one for odd and one for even voltage level changes. Right? So here, for example, I have 2 changes, which is even. So here it's even. So then I have 4 zeros. So I'm going to interpret the 4 zeros as B00V. Then I have 1. 1 is always opposite the previous non-zero voltage. Right? So if this is positive, then this should be negative. If this is negative, this should be positive. And then I have 4 zeros after that. So how many changes did I have since the last substitution? Remember, since the last substitution. In that case, it's 1. 1 is odd. Then I'm going to have the other substitution. For the case of odd, I'm going to replace this with 000V. V stands for violation. So again, 000, and then V, which is the same level like the 1. Right? And then after that, I have another 4 consecutive zeros. So at this point, I'm going to interpret this as a new 4 zero patterns. How many changes do I have here? 0. Since the last substitution, I have no changes. 0 is even. Right? 0 is even. So I go to the substitution B00V. So B stands for toggle or binary, or I have to flip the voltage level. And then 00 and then V. So V always means that take the previous non-zero voltage and put it as is. That's what violation means. And B means always look at the previous non-zero voltage. If it's positive, then make it negative. If it's negative, then make it positive. Right? Okay? So that's always the case. But here, instead of having one substitution for all cases? No, I divided that into two cases. One substitution is fit for even change of voltage levels, and the other one is good if I have odd changes of voltage levels. And what this tries to do again is to try to balance the changes, to make it always even. The changes should be always even. Okay? Any question? So that concludes the digital transmission. And by digital transmission, we mean that we try to convert the digital data into digital signal and transport or perform the transmission of the digital signal in the baseband. Okay? And we said that this is good if the channel is a low-pass channel, right? If the channel is a low-pass channel, which means that it kind of, it passes the low frequency levels or the zero frequency component. Although we have found after that this still causes some trouble if I have some line coding schemes like NRZI or some line coding schemes that have high power and the zero frequency component. This still causes a problem even for low pass channels. Okay? So if your channel is a band pass channel, an example of this, as we said before, is what? Wireless, bravo. What else? ADSL. Okay? So sending digital data over ADSL, that's a low pass, because that's a band pass, because if I send it in the frequency, in the zero frequency component, guess what will happen? It will interfere with what? With our voice. Because we're trying to send the data and the voice over the same line, so I have to have separation. Right? So we talked about that before. So in this chapter, we'll talk about some methods that are used for transmission of digital signals over bandpass channels. Okay? So we have some digital data, zeros and ones, still talking about zeros and ones. Okay? And my channel is a bandpass channel, which means that it does not have low frequency components. I have to shift the not only do I have to get rid of the DC component in that case, I have to shift the whole signal in the frequency domain very far away from zero. Okay? So I cannot afford to have any low frequency at all. So the channel itself will have smaller bandwidths or a specific bandwidth which is shifted away from the zero. So in that case, I need to convert the digital data into analog signal, into completely analog signal. So if we go back to the analog signal, we talked about the analog signal as in two categories: the periodic signal and non-periodic signal, right? And then we said periodic signal can be composite or simple, right? So what I will try to do is that I will try to use as much as possible the periodic simple signal as much as possible to try to shift the frequency of the digital data into the frequency domain away from the zero frequency. So the way to do that is using one of these techniques. So in general, what I will try to do is that I will take a basic analog signal. What is a basic analog signal? A basic simple analog signal, like what? Sine wave. Bravo, Alex. Like sine wave. Okay. And then I will change this analog signal based on some information from the digital data. Because if I send a sine wave, this means that for sure I'm sending high frequency, which is away from the zero, right? But then I have to do some changes to convey the information about the digital data. So if, for example, if the digital data is 0, then I have to send a sine wave with a particular shape. If the digital data is 1, then I have to send it with another shape such that the difference between the shapes is actually clear for the receiver to say, okay, this shape means 0, this shape means 1. If I do that, then if the basic frequency of this sine wave is away from 0, this means that I essentially created some kind of a bandpass signal which is away from the 0 frequency component. So what are the basic characteristics in the sine wave that I can use for that change? We talked about 3 major characteristics for any sine wave or any analog signal, which is what? Bravo, amplitude, frequency, and phase. Okay, so these techniques uses different combinations of these characteristics, as simple as that. So the first one tries to lay amplitude shift keying, tries to change the amplitude of the sine wave based on the digital data. Okay. The second one tries to change the frequency of the sine wave based on the digital data. The third one tries to create some kind of change in the phase of the sine wave based on the digital data. And then the last one creates some kind of a combination between 2 of these techniques. Try to change the phase and the amplitude. Okay, that's why it's called quadrature amplitude modulation. So it takes into consideration both the amplitude and the phase. So that's in summary what this chapter talks about. Then what we will do is that we will go through each technique, and then we'll try to again calculate some measurements. Like, for example, what is the signal rate for that technique? How do we calculate the bandwidth based on the signal rate? And we know from Nyquist and from other theory that how to calculate based on the signal rate, how to calculate the bandwidth. We know that the minimum bandwidth is basically the signal rate, okay? But then I can go above that to a certain extent, like we will see now. And then we'll try again to evaluate each of these techniques based on certain criteria. What is good here? What is bad? I mean, is the performance of this technique good from the noise perspective? So if I have noise on the channel, what is the effect of the noise on this technique? Okay. So as we said, so we're trying to convert the digital data into analog signal, and for that we will use one of these fundamental characteristics, the amplitude, the frequency, and the phase, or sometimes it's a combination between 2 of these. So the sending device produces a high frequency signal, which is based on the sine wave, which is a high frequency signal, and we call this a carrier frequency. This is the carrier frequency. The receiving device will then use some kind of a frequency detector to try to recognize whether this frequency represents 0 or 1. Okay? Type. So the simplest form of this is what we call binary amplitude shift keying. By binary, we mean that, again, we consider 1 bit. Can we consider more than 1 bit? Still, yes, of course. So we will interpret the 1 as a sine wave with an amplitude of V, whatever that V is. Okay? And we'll interpret the 0 as sine wave with amplitude 0, which is a 0. So this is what we call on-off keying. On-off means that if it's 1, I'm going to send sine wave. If it's off, then I'm going to send 0, which is again a sine wave with amplitude 0. Okay? Type. So what is the signal rate here? If I have, again, so if I have the 1, 0, 1, 0, and so on, then again the same equation applies. What is the value of R here? I'm interpreting each one bit as one signal path, one signal element. This is still one signal element. Okay? So in that case, R is 1, which means that the signal rate is C multiplied by N. Okay? And the worst case for C is 1, which means that the signal rate is in the worst case is N. So the signal rate equals to the data rate. What does the signal rate means? The signal rate is the number of different signal elements per second. And that turns to be N in the worst case. So the number of signal elements in second is N. This is the worst case. Okay? Then what is the minimum bandwidth? The minimum bandwidth is actually based on what we have studied before. The minimum bandwidth is the signal rate. Okay? The minimum bandwidth is the signal rate. So the channel, in order for the channel to pass this type of signal, at minimum, I'm going to have a bandwidth which is equal to the signal rate, which is N. Okay? So that's what we have studied before. So nothing new here. So typically, the sender will use some kind of filtering circuit which generates a signal which is above the minimum bandwidth. Okay? And that's why we have the factor D here. So D, if D is 0, this means that I have the minimum bandwidth, which is the signal rate, which is N. Okay? So if D is 0, this means that I have perfect filtering, which is not practical. So if D is 0 here, then I have the minimum bandwidth, which is the signal rate, which is N. But typically D is somewhere between, again, 0 and 1. So if D is 1, this means I have a lousy filtering, and the bandwidth requirement will be double the signal rate. So D is somewhere, again, like the C factor. D is somewhere between 0 and 1. But remember here, the D is accumulated to the 1. So 1 plus D times S. So the typical bandwidth here is 1 plus D times S, where D compensates for the imperfection of filtering and modulation circuit at the sender side. Okay? It's something that has to be given, like C. So we have to give you what D value is. Otherwise, you cannot calculate the bandwidth. And again, if D is 0, this means I'm hitting the minimum bandwidth. But then, in order for me to hit this minimum bandwidth, I have to have perfect circuit and perfect filtering and modulation, which is not practical. That's why I have to push D a little bit. So D, مثلا 0.5, 0.3, something like that. Okay? And the other important aspect is that, remember now that this carrier frequency is the frequency of the sine wave. So the bandwidth is the signal rate multiplied by 1 plus d, right? But the center frequency here is the frequency of the basic sine wave. So this means that now I have a bandpass signal. It's not anymore a low-pass signal where I have some zero frequency component. I shifted the signal in the frequency domain. Okay? So the signal will now be shifted in the frequency domain around the carrier frequency. And this carrier frequency is the frequency of this sine wave. Right? Okay? So this is the first and the simplest form for analog transmission, which is what we call on-off key. Okay? So this turns to be very simple in terms of implementation, as we will see. It's just a sine wave, and if I have 1, then I multiply 1 by the sine wave, which gives me the exact sine wave as is. If I have 0, I multiply it by the sine wave. 0 multiplied by anything is 0. Then I generate a sine wave with amplitude 0. So it's very easy to implement. I just multiply the actual data multiplied by the sine wave, and that's it. I don't need to do anything special in that case. So the implementation for it is easy. That's an advantage. Okay, what is the disadvantage here? The disadvantage here is that this technique seems to be very prone to noise. Because inherently, noise affects the amplitude more than anything. The noise affects a lot the amplitude. Okay? So this signal, again, when it gets transmitted over any type of medium, the amplitudes will change. Okay? So this signal the sine wave will change in terms of amplitude. I have two types of noise that can affect the sine wave here. I have attenuation, okay? So the amplitude will change, okay, but the shape will be kept the same. This is the attenuation noise, right? And I could have other types of noise like thermal noise or any other type of noise which can essentially change the shape of the sine wave itself. Luckily, if I change the shape a little bit, then I can still distinguish the sine wave from the zero, right? So it's still, as long as I have any change in the shape, I can still recognize this as not zero, which is the other possibility of zero is 1. So I can still detect it. But the attenuation noise is very critical in that case. Right? So any change in the amplitude, like if I have sine wave like this, and then I have 0, sometimes this cannot be detected as an actual sine wave. If the amplitude is very small, then I'm gonna interpret it as 0. And this happens no matter what you try to do. And that's why we say that, for example, for UTP, the length is 100. Why? Because after 100, the signal becomes very small. You cannot actually detect the 1 from the 0. So just by sending any type of signal through the wire, the attenuation happens. I can try to use some filtering to enhance to compensate for another type of noise. But the only way to compensate for this is to create some kind of amplifier. Is to have amplifier, okay? Which is what we call nowadays, مثلا الhub, مثلا, or any type of bridge or something. This amplifies the signal. But in any case, in normal conditions, attenuation affects the on-off key drastically. Okay? So it's easy to affect the amplitude more than the other two types of characteristics, which are frequency and phase, as we will see. So the motivation behind using another characteristic is that the amplitude of the signal seems to be very prone to noise. So again, the implementation of on-off keying is very easy. So we have the NRZ, or the basic binary line coding scheme. So the 1 interpreted as positive voltage and 0 is interpreted as 0 voltage. So the basic line coding scheme, and then instead of sending this signal as is, which what we have found out that this has all types of problems, including high power, including DC component, including synchronization, including everything. Okay, so instead of doing that, I'm going to consider that my channel is bandpass and I'm going to send an analog signal. So in that case, I'm going to send the signal as a composite modulated signal using the sine wave. So this oscillator will create the sine wave with fixed frequency, which is the Fc. And then if the data is 1, I'm going to pass the signal as is. If the data is 0, I'm going to pass 0. As simple as that. So the implementation is very easy. And the bandwidth is given by this formula, which is a 1 plus d times s, where s here is n. So here s is n, right? So, which means that the minimum bandwidth is s. And that happens, as we said, using perfect circuit, where the filtering is perfect, and in which case d is 0. But this is not always the case, and this is what we call the maximum bandwidth. Okay, so the maximum bandwidth for the modulated signal, for this modulated signal, will be 2s. And this happens if d is equal to 1. And d is always between 0 and 1. Okay? So so we have an available bandwidth of 100 kilohertz, which spans from 200 to 300. So it's basically, the signal is basically something like this. So from 200 to 300. Okay? And the bandwidth is 100. Okay? So, which means that, what is the carrier frequency? 250, bro. So the carrier frequency is 250. Okay? The question here is what's n? Or what is the data rate I can send? What is the actual data rate I can send using the ASK or on-off keying or amplitude shift keying? So what are the carrier frequency, which we have answered, very easy, and what is the bit rate if I were to use ASK? And d is equal 1. D is equal 1, which is the worst case. This means that the bandwidth which is a 100 equals 2s, right? And s is n, because r is 1, right? So in that case, basically n is 50, right? Very easy. What we have talked about so far for the on-off keying considers that the line or the medium of communication, which let's say it's a wire, okay? This wire is used for communication in one direction. So if that wire is used for full duplex communication, this means what? This means that I have transmission from the sender to the receiver and from the receiver to the sender at the same time, right? So it's a two-way communication, and they happen simultaneously. So in that case, I have to separate one direction from the other. And one way of doing this is to separate the two directions in the frequency. Okay? So in that case, I can use from the sender to the receiver, I use a sine wave with a particular carrier frequency, which is Fc1. And from the receiver to the sender, I'm going to use a sine wave with a slightly different frequency, Fc2. So in this case, the two signals will not interfere with each other. And you can separate one from the other easily by using a filter, right? But in that case, the exact same bandwidth I used, which is 100 kilohertz, I used for one direction, which resulted in a bit rate of 50 kilohertz. Now it's used for two directions, right? So the bit rate from each direction will be half, naturally. So I don't have to do the whole math, but will be half, right? So if D on both sides is 1, right? This means that I can have one sender sends to the other node, and the other node sends to the sender at the same time, using full duplex communication, but the data rate has to be half. So on each direction, I can send only 25 kilobits per second, because the bandwidth of each one will be 50 kilohertz. So this 50 kilohertz equals 2s, and s is n. So the bit rate on each direction will be 25 kilobits per second. Okay, so as we said, changing the amplitude is very prone to noise, particularly for a special type of noise, which is the attenuation noise, which happens all the time. Any signal that gets traveled over any type of medium, it loses energy, no matter what you do. It loses energy. So instead, what I'm going to do is that I'm going to use the frequency as another alternative to send the analog signal. So in that case, simply I'm going to send the one with a specific frequency and the zero with another, with the same sine wave, but with a different frequency. Okay? So this essentially means that this signal corresponds to one signal here in the frequency domain, and the other signal corresponds to this, and then I'm going to have to separate both in the frequency domain. So if I have this frequency and this frequency very close to each other, what will happen? This means that this will be interpreted in the frequency domain as interference, which means that those two will interfere with each other, will overlap. And it will become very tricky for the receiver to separate or to recognize that this is 1 and this is 0. Okay, because if I have some type of noise, like if I have, for example, thermal noise or impulse noise or something like that, these type of noises, they actually change the shape of the signal, not only the amplitude, they change the shape. Changing the shape meaning changing the frequency components of the signal. Okay? So if the frequency component of the signal is very close to each other, it's going to be very tricky for the receiver to recognize one from the other. In other words, I have to have some separation between those two signals in the frequency domain as much as possible. As much as possible. And this is what we see here as a gap. So see this gap? This gap is actually the difference between the frequency of this signal and the frequency of this signal. Okay? So this gap here corresponds to the difference between the two types of signals in frequency. Okay? So, so if I have F1 and F2, I need to be able to separate those two frequencies from each other as much as possible, because the more separation I have, the better the quality of the reception will be, because I will still recognize one from the other even with the existence of noise. So as we have discussed before in ASK, the bandwidth here, the bandwidth on each one, because each one is actually a sine wave, and R is 1, right? R is still 1 because I'm actually interpreting each bit as a signal element, right? So R is 1. So the signal rate for this signal is S times 1 plus D, right? So the bandwidth is S times 1 plus D. And the bandwidth of this signal is, again, S times 1 plus D. And then I have to separate the two signals, right? Using this delta frequency. So this is what we call 2 delta D. 2 delta D. And if 2 delta D increases, is getting large, this is good or bad? From the reception point of view, this is actually good. But it's bad from another aspect. Why? Because it increases the bandwidth, the overall bandwidth. Remember, the overall bandwidth is this. This is the overall bandwidth of this composite signal. Right? So as 2 delta F increases, this will enhance the reception quality. It will enhance the reception quality. And that's why we have like FM. Why we always tune to FM and not to AM? AM is amplitude modulation. صح? FM is frequency modulation. And FM always has better quality, صح? On the radio, when you go to FM, you hear better quality than AM, right? So that's based on this concept. So FM tends to have larger frequency, but better quality. Okay, so that's by default. So by increasing 2 delta F, I'm essentially increasing the bandwidth, but at the same time, I'm enhancing the quality of reception. What is the minimum value for 2 delta F? That's a good question. So I have 2 delta F is the difference between the two carrier frequencies of these two signals. Okay? What is the minimum 2 delta F? What is the minimum 2 delta F? What is the minimum of this?
There is only one frequency.
If there is only one frequency, I always have at least 2 frequencies because I have 1 and 0. So I have to have 2 frequencies. The number of frequencies here equals to the number of bit combinations that I have. I have 2 states, then I have to have 2 frequencies. So as we said here, the more I increase 2 delta F, the better the quality will be, but the bandwidth will be increased. So make it small. Okay? What is the smallest value of 2 delta F? I will try to make this gap 0, right? Can I make it less than that? If I make it less than this, they will overlap, right? So what is minimum 2 delta F?
F1 by 2 plus F2 by 2.
لا هو what is the width of this whole what is the width of this? What is the width? الباندويث, right? صح? لو S times 1 plus D, right? What is the width of this? S times 1 plus D. So I take half of this and half of this, صح? And this will be minimum, the minimum 2 delta F. What is the half of this and half of this? It's S times 1 plus D, صح? Half plus half is 1. So the minimum 2 delta F is actually S times 1 plus D. I cannot make it less than that. صح? So the bandwidth here is basically, the bandwidth is this half plus this half plus 2 delta F. Why do I have to make it this way? Because I don't know what 2 delta F is. This is something configurable. I can increase it or decrease it based on my need, right? So this is a function of 2 delta F, and it's up to you to make this large or small. And as we said, the minimum is S times 1 plus D. So I have half S times 1 plus D and half S times 1 plus D plus 2 delta F. صح? This is the bandwidth. So the whole bandwidth is S times 1 plus D plus 2 delta F, which is at the minimum is a 2 times 1 plus D times F. This is the minimum. So the minimum bandwidth for Fsk, the minimum bandwidth of Fsk is essentially double the bandwidth of Ask. صح؟ حد مش متابع الديريفيشن very simple derivation. يعني هو basically, so the bandwidth is half the on the other side, on either side I have half, and on the middle I have 2 delta F. So it's basically half 1 plus D times S plus half 1 plus D times S plus 2 delta F. Right? So so this is coming from this part here. I have half of this, and then I have half from the other side, and then in the middle I have 2 delta F. So if I sum those three values, this constitutes the whole bandwidth of the entire composite signal. And as we said, the minimum 2 delta F is 1 plus D times S, so the minimum bandwidth is double Ask. Okay? So a very quick example, if we have an available bandwidth of 100 kilohertz, the same bandwidth that we had for Ask, which remember resulted in a data rate of 50 kilobits per second for one direction, not even for the full duplex. So what should be the carrier frequency and the bit rate if we modulated our data by using Fsk in that case? And still D is 1. So what I'm trying to do is to compare the data rate. Of course, I know in terms of quality, Fsk is going to beat Ask, that's for sure. This is much more resistive to noise. In terms of quality, it will be good. But the cost that I had to pay now is that we have the modulated signal Fsk, and here the bandwidth is simply the bandwidth, as we said, is 1 plus D times S plus 2 delta F, and the minimum 2 delta F is again 1 plus D times S, and if we have D equal 1, this means I end up with a 4S, which means R is equal to 1, صح? which equals to 4N. So if the bandwidth is 1 kilobits per second, 1 kilohertz, this means that the data rate is 25 kilobits per second, which is half what I can send using ASK. So the cost here is that I have to send slower data rates. This is the cost in order to increase the reception quality. طيب. The implementation for the FSK is a little bit more complicated, because now I have to have a signal generator, an oscillator with variable frequency. Okay, and this is what we call voltage controlled oscillator, or variable frequency voltage controlled oscillator. And that's a complicated circuit compared to a multiplier. Like for the case of ASK, I just multiply the carrier signal with the amplitude of the digital data. That's it. But here I have to have a more controlled, voltage controlled circuit. So if the value is 1, this means I can use the carrier signal with no frequency change. If the value is 0, then I have to increase the frequency or decrease the frequency, whatever. So this creates this composite signal with the characteristics that we talked about before. So we'll finish with this example. This example talks about a complicated signal. So here, what we're trying to do is that we're trying to interpret each 3 bits as an analog signal element. So for each 3 bits, I'm interpreting this using the signal element. So I have from 000 all the way to 111. So if I were to use that using ASK, what I'm going to do is that for 000, I'm going to send a specific amplitude. For 001, I'm going to change the amplitude a little bit, and so on. Right? In that case, I have to have variable frequency. And how many frequencies do I need in that case? How many carrier frequencies do I need? 10. Okay? 8. I have to have, because I have 8 combinations. Right? So each signal element will have to have a distinct frequency which represents this bit combination or this bit pattern. So I have to have 8 different frequencies. So between each 2 frequency, I need to have 2 delta F. Right? So what is the number of frequencies? 8. What is the baud rate for each of these signals? Well, the baud rate is the same like the bit rate. So if I have a bit rate of, we need to send 3 bits at a time. What is R in that case? Yeah, the number of data elements divided by the number of signal elements. So I have to represent each 3 bits as one signal element. So what is R? 3. صح? So S, what is S? So since R equal to data elements divided by number of data elements divided by signal elements, it's 3/1. So this is R. What's S? S is the worst case is N multiplied by 1 over R, which is what's N? A bit rate of 3 divided by 3. So S is 1 megabaud, because this is 3 megabits per second. So the signal rate is 1 megabaud, and this is a typo, by the way. So it says 3 divided by 3 is 1000 megabaud. So it's actually 1 megabaud. Okay, so you can correct that. This means that the carrier frequencies, I have 8 carrier frequencies for sure. I need to have 8 carrier frequencies. So what's 2 delta F? Well, I have to give that to you. But I can tell you, for example, okay, use the minimum 2 delta F. So I know minimum 2 delta F is 1 plus D times S. So we know that S is 1 megabaud, and if D is equal to, what is D here? D is equal to, let's say D is equal to 0. This means that the minimum 2 delta F is 2 megahertz. 1 megahertz. The minimum 2 delta F is 1 megahertz. This is the minimum, assuming that D is is 0 and I have the minimum 2 delta F. So what is the shape of this signal? So what is the shape of this signal now? So the shape is, it looks like this. So at the frequency F1, I'm going to have a signal like this, and this signal is 1 plus D times S. If D is equal to 0, then it's S, and S is equal to N, which is in that case, so I have to have 1 here, 1 plus D times S. And S, as we said, is 1 megabaud, so this is 1 megahertz. And then another one, which is 1 megahertz. And then another one, and then another one, and then another one, and so on. With, this is F2, so the 2 delta F here is 1 megahertz. So if this is half megahertz and this is half megahertz, so the minimum 2 delta F is 1 megahertz. Right? And I have to create 8 of these. Right? So the whole bandwidth of the entire signal is what? I have 8 of these, each one with width 1 megahertz. So what is the entire bandwidth? 8 megahertz. Okay? So let's see how this looks. So if I have around carrier frequency, that the carrier frequency of the entire composite signal is at 10 megahertz. So this is the carrier frequency. So this is fixed. So I have to split the whole signal into 2 halves around this carrier frequency. Since I have 8 and 8 is even, so I have to put 4 of them here and 4 of them here. So this is the carrier frequency, 10 megahertz. Minus 1 megahertz, this gives me this signal and this signal and so on. And then I go at each signal and I put the carrier frequency for each sine wave, which is in the middle. So this means that F1 will be at 6.5 megahertz, F2 will be 7.5, and the difference is always 1 megahertz, which is the minimum 2 delta F. So if I have 4 bits at a time, this means that I have to have how many frequencies? 16, which means that the bandwidth will be divided evenly. Okay? So any question? Okay, so we'll stop here, inshallah.